So thank you so much, the organizers, for inviting me to talk. I'm really enjoying the conference, and I'm excited there's a whole nother day. What I'm going to talk about today is computational models of curiosity and learning. That's most of what my lab works on. You can think of curiosity as the driving force that motivates an infant to seek out and learn from things in the world. It's sort of the gatekeeper of knowledge. And that's important because babies know very little. Your mental model of how things operate in the world is what you use to make decisions. If you want to make good decisions, it's very important that you have as accurate a mental model as possible, and curiosity is the driving force behind that. I'm going to get to the computational models of curiosity, but before I do that, I want to start with a study that I think does a good job of demonstrating why the decision-making mechanisms are important and how expectations shape your decision-making process. A couple other people have made reference to these studies before. These studies were based on the Stanford marshmallow experiments. These studies, in case you don't know, were done with 3 to 5-year-old children. The children were given a choice. They could either have one treat now, most canonically a marshmallow, or if they were willing to wait some undisclosed amount of time, they could have 2 later. What was notable about these studies is that the majority of kids failed to wait, but the kids who did wait, I was like, it's not these first set of studies that really got people excited about this work. It's that later they found that longer wait times, the earlier you waited and the longer you waited, the better you went on to do in life. So longer wait times were correlated with things like college admissions testing, standardized testing, how many friends you have, your body fat, your self-image, your self-confidence. The idea, how these were popularly interpreted, was that it was self-control that was driving these effects. So if you're a kid that has a deficiency in self-control, you can't resist the immediate temptation to eat the marshmallow. You go on to be the kind of kid who can't delay the temptation of playing or watching TV instead of studying for your exams. Kids who lacked self-control in the marshmallow task, the idea is that they would go on to lack self-control later in life, and this would cause them problems. We were interested in testing a different alternative hypothesis, which is that their expectations could drive their decisions. The difficulty here is that expectations are not directly observable. So to get around that, we did not measure them. We instead just manipulated them in the lab. It's much easier to manipulate expectations than to measure them, it turns out. And the way that we did that is we prefaced the classic marshmallow task experiment with an art project task that was designed to provide kids with evidence about how reliable or not reliable the current environment was. So we randomly assigned kids to one of 2 conditions. In this art project task, what they were told that they were going to do is to make a cup like this. There were 2 instances in which they were given a choice between the art supplies that they were going to use. So they were either given a choice to immediately use a low-value art supply, in this case use crayons, or if they wanted to wait some undisclosed amount of time, a big new art set. If they were in the reliable condition, the experimenter left the room and came back with the promised items. If they were in the unreliable condition, the experimenter came back and apologized that they didn't have the big new set, but helped them use the lower value art item. One instance is maybe a fluke. So we gave them one other similar choice in the process of doing this art project task. They either had a small sticker immediately available, or if they wanted to wait, they could have many better stickers that either did or didn't arrive depending upon the condition that they were in. And after we did that, we provided them with evidence. We did the classic marshmallow task experiment. We cleared the room out of cleared the art supplies out of the room and told them it was snack time and gave them a choice. So let me show you what this looks like.
You finished just in time, because you know what time it is now? It's snack time. Do you like snack time? Yeah? All right, well, listen. So for your snack, you have a choice. Look what I've got.
Marshmallow.
Yeah, so wait just a second, let me explain. So you can either eat this one marshmallow right now, or if you can wait for me to go get it from the other room, you can have 2 marshmallows instead.
I want 2 marshmallows.
You want 2 marshmallows instead? That's what I thought you would
That was a
say.
very popular choice. So all kids chose to wait for 2 marshmallows. And then, just like in the classic task, we measured how long before first taste. That's it. Okay, I won't wait for the reliable condition kid to eat the marshmallow. Instead, I will skip straight toward the data. Those kids were pretty typical, even though they were not real kids. It's like those were demo kids that we filmed after. There's a camera in the room that would be distracting. In the unreliable condition, kids waited an average of about 3 minutes, as opposed to in the reliable condition where they waited 12 minutes. Now you can compare this to the wait times in the original Stanford marshmallow experiments with similar conditions. That's about 6 minutes. So it's kind of tempting to think maybe you like push it down or up, but there's a lot of other things that may have been different. The important thing to note here is that the evidence that they got about whether waiting would be worth it or not in this context made a difference. It pushed around their wait time, thus making it unlikely that the effect is entirely driven by just your capacity to control yourself. Why this matters. We think this provides a viable potential alternative for the longitudinal correlations. It could be that it's not self-controlled that's driving these effects. We have lots of evidence that when your life is unstable, things are pragmatically harder. It's like if you're moving around a lot, it's hard to do well at school. It could be that what the marshmallow task was actually measuring was how stable your life is, and it's really that life stability that is causing those longitudinal correlations. Another reason I like this study, and I open with this one, is because I think it's a good demonstration of behavior that appears to be impulsive actually being quite sensible. It's important to, when you're drawing conclusions about a kid's capacity, especially their capabilities, that you take under consideration what their assumptions are and what their expectations are. Finally, I think this is a pretty clear demonstration that their decisions to wait are at least partially modulated by their expectations. If they're given evidence that waiting will pay off, they wait a lot longer. It's like they're way more likely to wait. So I mentioned that what I'm mostly going to talk about in this talk is how expectations influence other sorts of decisions, specifically attentional decisions. That's most of what my lab works on, and I want to start by talking about the set of studies that got us started on this line of inquiry. I'm going to start by showing you guys an example of an infant experiment. We designed these so that they would be easy to model, that they were quantitatively tractable. These displays start with an attention getter, as many infant studies do. Whoops. See if I can make that one play. Sorry, I lost my clicker. Okay. There we go. Once the infant was looking, there's 3 boxes, each containing 3 things, and they pop out in some order. And how it worked is as long as the infant continued to look at this sequence, the sequence continued to unfold over time. I'll show you guys just one more to give you an idea. When the infant looks away, attention getter comes back, and we do another sequence, and so on and so on. Let me skip to showing you guys an example of a baby actually doing it, because it's cute, and it wouldn't be a developmental talk without it. So as long as she keeps looking, things keep unfolding over time. So at each time point, she either continues looking or she looks away. Oh, that was close. She didn't look away. She's much more amused than the mom. Okay, so she looks away. 1 second criterion. It turns off, the laughing baby comes up, and she resets. And then we do that over and over again. So that's what the data that we had looked like. And what we did with this was we measured when infants terminated their attention using that setup, and then represented their expectations using a computational model. This is where the modeling comes in. How the model worked, it was a probabilistic model that took event counts. So let's say the baby has seen 3 A's and a B. Their observations look something like this, but hopefully you have the intuition that your expectations are not just governed by what you've seen. Before any of the boxes started opening, most people have have the intuition that they're all equally likely. So that's also a part of the model. We call that the prior belief, which you can think of in a simplified form as just being a count of 1 on each of the objects. You combine that through things that are described in the paper, but I'm going to go over quickly here, and you get this updated belief. And it's this updated belief that allows us to compute how predictable or surprising we think an ideal learner and the infant should find an event. So if the baby thinks it's mostly A's and sees an A, well, that's pretty expected. We'd expect that that would be pretty predictable. If, however, the baby thought that C's didn't occur very often and then sees a C event, that would be very surprising, and that'll go to the other end of the spectrum. And what you do is when you do this is you get this nice U-shaped function where infants are far more likely to look away at either very predictable events or very surprising events, and they're least likely to look away at events of intermediate surprisal. This one is for the unigram statistics. You might wonder if maybe that's not quite the right model. Maybe what you care about is not just how often A versus B versus C. Maybe you care about, given that I just saw A, how likely is it to be A again? For the transitional statistics, it's like you get this same shape function. You get it for different types of displays, not just for visual displays, but also for auditory sequences, and even within individual infants. So all of these other plots I showed you were done at the population level. You might worry, I know I'd heard people talk about before, the possibility that maybe you have some infants that really prefer very predictable things and some infants that prefer very surprising things. You average them together, it looks like a U, but it's not. It looks like that is not the case. You can recover for most infants this significant U shape. So why? It's like, why the U? We were not the first people to suggest that there might be a U-shaped relationship between kids' expectations and their interest. This is a very old idea, and I cited just a few of the many people who have talked about this sort of possibility. In a nutshell, the idea is that you want to seek out things that have learning value for you. And if something is overly predictable, that could indicate that it entirely overlaps with what you already understand. If I'm going to pick out a DVD, it's like this one here containing information on the ABCs that my infant son has seen 8 million times, it's like, is entirely redundant with everything that I know. There's no learning value there for me. On the opposite end of the spectrum, you might think that the more new information, the better. There's a DVD in a language that I do not yet speak on hand gliding. Maybe I could learn Hungarian and I could learn hand gliding, but hopefully you have the intuition that probably I can't. I'm missing base levels of representation to make sense of it. I'd be better off sticking with something that's in the middle, that's a little bit distinct from what I already understand, but not so distinct that I can't get any traction. So that's where we started. Sorry, one second, guys. And I mentioned that our interest here was in understanding the relationship between attention and learning. A U-shape has been theorized to be useful for learning for this reason, for these intuitive reasons. But we actually didn't measure learning in those first set of experiments that I talked about. So what my lab has been working on since then is studying how this mechanism interfaces with dynamics of real-world learning situations. And where we started in doing that was doing some modeling work. This is work that I've been working on with Maddie Pelz, who is currently a graduate student at MIT. And the idea of this project was to formalize a theory that related attention to learning. What we wanted to know is what would a rational learner look like when trying to maximize potential information gain among many possible objects. So this first model I'm going to talk about is purely theoretical. There's no behavioral data. And just like before, I'll go through the intuitions behind it. There's a few key components. The first one is there's an ideal learner. And then there's a toy world with multiple possible objects to attend to. The goal of the learner is to maximize learning overall, since that's what we're theorizing that infants are doing. a couple components that I should tell you about. As like one is the learning curve. So this is this represents all of the information you could possibly learn about an object versus time. And the function we chose to try out is a Gompertz, which is characterized by a slow startup as you're first starting to learn about an object, and then a diminishing return as you approach everything that you could possibly learn about an object. Another important component of the model is the information decay parameter. The world is not static, so if you're learning about some kind of animal in a field, you can learn things about whether it's furry or has scales. You can learn about how it moves. Maybe if you watch for long enough, you can learn what it eats. But when you look away from that animal in the field, it doesn't stop moving. You lose information because it continues to do its animal thing. So this represents the idea that when a learner is not attending to something, there's information lost, both from changes happening in the world and also from forgetting. And we're going to use a power law decay to represent that part. OK. And then the third component is the decision process. How the model works is at each time point, it's going to compute expected information gained from each of the possible objects in the mini environment, and then make a decision about whether to maintain attention or to switch based on where it expects it can learn the most. And when you do that, you combine just those simple components, this is what you get out. So I'll walk you through this. There's 5 possible objects to attend to here. At time point 1, the learner knows nothing about any of the objects, so it doesn't matter where the learner starts. The learner picks one at random, in this case, conveniently object 1 or the yellow. It starts learning about that object, and as it approaches the diminishing return part of the curve, it now makes more sense to pick any of the other objects. So it picks at random from the remaining set of objects, in this case object 2, the green object, and starts learning about that one. But while it's learning about that one, it loses information about that first object because of the information decay component. So at some point, it makes sense to switch back and forth between those two. The same thing repeats for the third one. The same thing repeats for the fourth one. What you should get out of this is there's some interesting dynamics that emerge just from those simple components that I talked about. First of all, you'll notice that initially you spend longer looking at each object, whereas over time, as you've gained some information about the objects in your toy world, you start spending more and more time switching between them. Another thing that's important to notice here is that not all of the objects got attended to. It's like there's 5 in this set. Object 5 never gets picked up. At some point, depending upon the particular value of the information decay parameter, it makes more sense to continue maintaining existing representations rather than to pick stuff up forever. This is where we started, and what we've been doing since then is we don't intend this to be a perfect representation of how curiosity works, of how learners work, but it's a starting point to help us formalize a theory of curiosity that we can use for a number of things. What we've been doing is designing behavioral experiments to test to see to what degree these dynamics are true to how people learn. So one question that we started with is whether real learners exhibit attentional juggling. 1 second. We've done a series of experiments with both adults and infants where we give them sets of things and just look to see, is it the case that over time you get shorter looks as you're maintaining? For both adults and for infants, it appears as though this is true. So initially, you're looking long at each object, and then you start spending more time switching between the objects, and you spend less time looking at each individual object in the set. Another question that we've looked at is pertaining to the pickup decision. So how do real learners choose what to pick up next? I'll remind you again about this learning curve part of the model. So this is all the information you could learn. If a learner in the real world has a choice between A and B, it could be that people pick just like our model did, that people pick based on the expected rate of information. Here, if you have a choice between A and B, the model would choose A because that slope is steeper. So that's one possibility. People could choose A. It's also possible, though, that people could choose based on some other factor that's correlated with that rate, but not exactly the same as that rate. So one possibility is the information gap. This is an idea that's been suggested by people like George Lowenstein. It could be that people pick A, but they're picking based on the amount of information that they don't yet know. Interestingly, when we were scouring the literature looking for possible hypotheses to test out, another one that seemed to come up was this one, the almost knowing hypothesis. So these sort of theories are kind of like the ones suggested by Jerome Kagan and other developmentalists. It could be that you pick based on the amount of information that you don't know, but you go for ones where you can learn everything quicker. So you'd pick B here. So in a series of studies done by Shirlene Wade, she intentionally decorrelated these factors to look to see what better explains how real people choose. We were expecting it to be rate, like our model, and it does trend in the expected direction. So this is your mean curiosity when the information is presented fast versus slow, and learners are more curious when it's faster versus slower, but in multiple experiments now, although it trends in the right direction, it's not nearly as as big of a difference as we expected to see. Information gap, however, is like, does a really good job of explaining people's curiosity. So for this study, we gave people podcasts. They got different amounts of the podcast at different speeds that were both within the range of their processing abilities. And what you see here is that people are most curious after the first sentence, a little less curious after the second, a little less curious after the third, a little less curious after the fourth. This is not just an effect that happens at the population level. Each dot represents a person here, and this is curiosity for an individual at sentence 1 versus sentence 4. As you see, all of the dots are above that line, meaning that individuals are more curious at the beginning when they've had very little of the story than when they've had a lot. So far, we found a robust effect where the less you know about something, the more curious you are. This is not what we anticipated finding, but it's interesting in light of things like clickbait. I was like, the day that we replicated this finding, we were all sort of confused because we'd expected rate to be much more meaningful, and then we went back to our browsers and did what good scientists do and procrastinated a little bit, and we started noticing that there's this interesting feature of clickbait where what rises to the top tends to be the stuff that tells you very little about what the content of the story is. So if you look at this first one, what these pilots do with dogs is one of the most brilliant things I've ever seen. There's not much there to tell you about what's going to happen when you click. Clickbait is generally not designed with any sort of cognitive theory of curiosity in mind. How it works is people try a lot of stuff, and then whatever gets clicked a bunch rises to the top. This is a feature that other people have noticed about what rises to the top, and it tends to be stuff that has what's called forward reference. It lets you know that there's something that you don't know. In other words, it creates an information gap. One other quick thing that I will mention, for these first set of studies, we were sticking with stimuli that was structured in a way that you were able to estimate how much information you didn't have yet. We used things like podcasts. But moving forward, we're also interested in understanding how curiosity works in cases where you don't have access to that information. For things like YouTube videos, where it's often very hard to estimate, I'll show you guys an example of one of those. So you know it's claymation. What's going to happen? What don't you know? Hard to know. There's a worm, right? Hopefully that was surprising. Nobody knew there was going to be a worm at the beginning unless you've seen this cartoon before. The idea here is that sometimes in the real world it may be hard or impossible to estimate what that gap size is. In that case, we found that surprise might act as a heuristic for allowing you to estimate that gap size. People are much more curious when they've just been surprised, which can indicate that there's a gap between what you currently understand and what you should. I'm going to wrap up with just my 1 minute left with talking about why we need computational models of curiosity, why they are important. One thing that you can do with them, there's a lot of interest lately in designing adaptive learning tools that optimize learning within individual users. That's not really possible to do well unless you understand something about the theoretical system. It's like understanding how things like working memory relate to learning and relate to what the ideal setup is really important as a back end for these sort of systems. That's one direction my lab is going. Another direction that we've been going in, originally our models were designed as just sort of a formalization for how curiosity and attention work in infants. But those same models that we designed to try to understand how infants work turn out to be useful for making robotic systems smarter. So I've been working with Pierre-Yves Odier on applying those same sort of models in robots so they can do more unsupervised learning. And then the last big direction my lab has been working on is using these models as a framework for understanding the neural correlates, the neural components underlying these sorts of processes. We don't understand everything we need to about things like, for example, how value is represented. On that note, I will wrap up. I want to thank the organizers, my lab, my funders. I know that this talk was brief, so if there's other things, I was like, all of the publications that I have, that my lab has, are on our website, our lab website, and my website. And please feel free to send me an email. Thanks. I'm going to step out here so I can see people.
Questions?
Thanks, very beautiful. Hi.
Thanks.
Yes. If I'm not mistaken, your data don't support the inverted U-shape, right? Yeah, it's more like a linear relationship, like the more surprising, the more curious, the less you know, the more curious, etc.
You mean that last set of stuff?
Yeah.
Yes, that's right. Although we didn't push it, I was like, they're all YouTube videos. So I was like, if you're watching a YouTube video and like a monkey leapt out of the screen, it might be that the range we're sampling in is not far enough. I was like, that's actually one of the things that we're currently, we're trying to get a handle on before publishing that paper. It looks linear in the part that we have, but we only have YouTube videos for that plot.
Right, okay. Yeah,
we need like somebody startling somebody watching YouTube videos, and that would maybe do it.
Yeah, because I think the example you gave yourself of the inverted U-shape, I think sometimes a confound there is that the situation where you don't know anything, it could be that you don't know anything because you're not interested, right? So then in that sense, I think that confound is maybe less in your studies where you basically don't, where you're not capitalizing on how curious you are about real-world events, but where you basically have a more lab-based setting.
Right, yeah, it's hard to know. This is a problem with trying to figure out what the true shape of the function is. You're always sampling in some range. The experiments in our lab, mostly it's been within a range of things that we can estimate your expectations for, which is pretty artificial and limited. I use the silly example of like a monkey popping out of your screen while watching YouTube videos, but that's like tractably, quantitatively, I don't know how much more surprising that is than a worm popping out in the actual video. So I was like, that's a good point.
Thanks.
So, hey Celeste, great talk.
Hi.
So one thing that your, especially the second set of experiments really reminded me of was foraging theory, right? Mm-hmm. Where there's the same sort of like stay switch cost to just looking for resources, where kind of presumably like more food is always better than less food. I'm curious if you have any ideas about how theories like that may be related to the work you're doing, and maybe especially if you should or shouldn't expect gathering physical resources to act like gathering information.
So I think of them the same way. There's an important sort of under subtext to the question you asked, which is, I was like, right now we're doing something which is a little weird, but I think the only way to do it, given that we don't have given our knowledge right now in the field, which is that we're collapsing two things that are very different in terms of how they're represented, which is external factors and internal factors. Some of those are about uncertainty. It's like what exists in the world. That's like more classically what you're talking about when you talk about a foraging task, what's out there. But there's another type of uncertainty too, which is your own uncertainty. If you detect something that is very different from what you expected, perception is not perfect. Perception is an inference problem. I was like, we just heard a talk about that. So it could be that if it's too different from what you're expecting, it's not right because of your internal noise too. Yeah, I was like, I glided over, but is a reoccurring, interesting problem that happens in the lab. I was like, the information decay parameter, I sort of referenced it, but didn't really go into it. I mentioned that it represents, for us in this very abstract theoretical formalization of the theory, both changes that happen as a function of the world. I was like, we'd expect that if things in the world are moving faster, I was like, if you're looking at a fox as opposed to a snail, I was like, the total number of things you can handle goes down. I was like, you'd expect that that would have an influence on your attentional system and your curiosity system. You should, for foxes, spend more time switching. It's like, and look at fewer things overall. But that same parameter also right now represents the internal component of that, which is your own working memory. I was like, how fast are you personally forgetting? We know that that's something that varies across people. We know that's something that varies across kids. Symbolically, we're collapsing those into one. That's convenient because of what we're trying to do. I was like, with the models, we're trying to understand the system. But neurally, I was like, the way that those things actually play out in the system you'd expect would be different. So I was like, this is definitely a computational level theory. We're not at the implementational level yet. But that's what you want to know if you really want to understand everything. Yep. Oh.
Hi.
I'm not calling on people. Sorry, John.
Thanks for a great talk. I actually wanted to jump back to your marshmallow experiments that you started out with, which I think is really cool. And I was particularly interested in the level at which you think the effects you're showing are playing out. So, for example, if you ask the kid, so if you, for example, you've given a kid twice you've shown them that if you're basically breaking your promises. The people in this lab are unreliable, don't trust them for anything in the world. You ask them when they give you this in the snack scenario, presumably if you ask them, do you think this person is really going to give you a second marshmallow after all of this that's happened? They may well say no. I don't know if you have data to this. And then for the opposite conclusion. I'm curious whether in the original study, if you had asked them, you would have seen a similar pattern, if you see what I mean. If the kids who would have said, no, I don't expect this, are the kids who wouldn't have waited, and vice versa.
We found that kids are not very good at answering questions about, we have tried stuff like that, not an experiment, but in other ones. Kids are not very good at articulating their expectations. I was like, what we found when you try to, every way we formulated the question, what you get out are their wishes. So they tell you what they wish would happen, and you can't get much else. That said, we have gone back and looked. There was a kid who was in the unreliable condition. I mentioned that all of the kids said that they would like to wait for 2 marshmallows, but then they didn't end up waiting. One kid that we ran early on said he would like to wait for the 2, and then he like narrowed his eyes and he looked at the researcher and said, "You better have 2." I was like, which there were facial expressions. That was the only kid that articulated a threat. But we got the sense, you get the sense from watching the videos, it's like they're looking skeptically. We coded the videos, it's like if we made kids in one condition happy and we made kids in one condition sad, that would presumably also influence the effects. It's like we had other measures to make sure that they were equally content in both conditions, but the eye narrowing, the like, this sort of thing happened for the kids in the unreliable condition and not the kids in the reliable condition. And a couple articulated things like that. Like I was like, a couple of them asked, "Are you sure you have 2?" Before making their choice. So yeah, you get the sense that they knew what was up. Yeah. back to your first question, which I kind of skipped over, we were thinking of it as a short-term effect. If we thought that giving a kid 2 instances of the world being unreliable, they would then go out into the world and be like, everything's unreliable, I'm never studying again. That would be unethical, we wouldn't have done that. It's like we were thinking of it as a very flexible thing. Since we ran that study, I've had the opportunity to speak to more evolutionary psychologists, and it has been pointed out to me that there's some forms of environmental instability which do cause long-term permanent changes. It's like mammals in food-scarce environments undergo puberty sooner, and they adopt a totally different mating strategy. Once you've gone through puberty, that's it. There's no going backwards, even if you're suddenly in a food-rich environment. So I think that there is a case to be made both for the system being somewhat flexible, like in some cases, but also probably we have evidence that for some things early experience matters more. So I think that's an unsolved question, what proportion we have there. Yeah.
Thank you.
Hi, so over here, hi.
Hi, Josh.
Hi, this is just a sort of a small question about your ideal learning model.
Yeah.
Where you had that sigmoid function, right?
Yeah.
I mean, in many learning models, whether it's simple statistical models or fancy Bayesian models or various neural networks, the learning curve looks more, doesn't have that initial inflection. It just sort of starts off steep and then gets shallower. Have you explored that kind of model? Or
we have played around a little with that. As like that component we haven't messed with as much as the information decay component. I think that there's a lot more work to be done in that area. I was like, that's a whole nother, what the right functions are to use for that probably depends somewhat on the task. It's not intended as, we're not trying to make strong claims about that being the way people are.
I guess what drew my attention to that was, I not really knowing exactly where you were going with the modeling, and I guess it's still to be determined, but it looked like, okay, well, if you're trying to explain some of the U-shaped curve stuff, it looks like there's sort of like a little bit of a U sort of thing built into that inflected sigmoid.
Yeah.
And that seems like the kind of thing you'd want to explain rather than build in.
Yeah, we were not, I was like, we hadn't connected those two more directly. We were starting, the intention was just to start with something reasonable that other people had used. The Gompertz was a common way of representing the process of learning in some psychophysics experiments, and then it was the most common one in robotic stuff. So since that was the most similar to the kind of thing we went, that was a starting spot, but that is not intended as the end-all be-all. I was like, the hope is to keep doing behavioral experiments and see where it breaks down. And I was like, one component to play around with is that particular component.